Now in this lecture we will see another estimation method, which is least square estimation method. Suppose x1, x2 to xn is our random sample, and the parameter theta is the mean of the distribution from which the random sample was drawn. We wish to estimate the parameter theta. Then each difference xi minus theta should be fairly small. A reasonable estimate of theta might then be chosen to try to make all the differences as small as possible. S is equal to sum of xi minus theta whole square, where I is equal to 1 to n. So if you see this over here in this last example, we also found this difference W, which was from the actual value and the estimated value, and here we are doing the same thing. We are getting the difference between the actual value and the average value. So, but here we have squared this difference. Why? So squaring the difference makes them all positive, so that possibly large positive and negative differences do not cancel each other out, and we do not get zero sum. Suppose that observations x1 is equal to 3, x2 is equal to 4, x3 is equal to 8 were collected in a random sample of size 3 from a population with unknown mean theta. So here we have got a sample which has got values 3, 4 and 8 from some population, and the theta of this population is not known. The mean of that population is not known. The observed sum of squared differences is given by I is equal to 1 to 3 xi minus theta whole square, where x1 minus theta whole square plus x2 minus theta whole square plus x3 minus theta whole square. We have to sum all these, and we just simply replace x1, x2 and x3 with these given values over here. So we get 3 minus theta whole square plus 4 minus theta whole square plus 4 minus theta whole square. And using the simple algebraic formula, we get 9 minus 6 theta plus theta square, 16 minus 8 theta plus theta square, and 64 minus 16 theta plus theta square. And after simplification, we finally get 89 minus theta square plus 3 theta square, or we may say 3 theta square minus 30 theta plus 89. Now let's assume different values of mean theta to find the sum of the squared differences. So we will just simply replace these values of theta in this equation. For example, for this first one, we will put theta is equal to 0. So 30 into 0 is equal to 0, and 3 into theta 0 square is equal to 0. So we get 89, and then we have 1. So we get 89 minus 30 plus 3. So we get 62, and so on. So we go up to 8, and after that we may go further, but we stop over here to see what happens. From this table, it looks as though the sum of squares is high for low values of theta from 0 to 4. As you can see, it is 89, 62, 41 and 26, and attains a minimum of theta 5. At theta 5, that is, you get the minimum value 14 over here when theta is equal to 5. After that, you see again it is increasing in the same order, 17, 26, 41. You can see it was decreasing 89, 62, 41, 26, 17. Then it is started increasing in the same order, 17, 26 and 41. So what we get, the minimum value at this theta is equal to 5, which is 14. After theta is equal to 5, the sum of the squares start to increase. This makes sense. Based on observations, the values 3, 4 and 8, a guess at an underlying mean of theta is equal to 1 is not a very sensible guess. If you look at just these values, then intuitively you can see that the average of these three values, 3, 4 and 8, cannot be 1. And average of these values cannot be 8 as well. So if you just simply add this 3 plus 4 plus 8, which is equal to 15, and divide by 3, then you get 5. So again, you can see that we have got this 5 over here. So this can be seen intuitively as well. And from this equation, we see that we get the minimum value at 5. When that value of theta is 5, we get the minimum value. So you can see from the graph that a minimum is indeed attained at the point theta is equal to 5 over here, and then it is like a parabola. The values are same. For example, whatever the value we get at 1 is the same as at 9 or maybe 10, something like that. So for a general random sample of size n from a population with unknown mean theta, the expression for the sum of squared differences may be written as, so how do we can write a general expression for this one, and it is very simple because we just use the a square minus 2b plus b square formula for algebra, xi minus 30 theta whole square. So we just simply expand it and we get this one. And the expression is minimized at sample mean theta is equal to xi over n. So all the xi divided by n, as we did over here. In this case, 3 plus 4 plus 8 is equal to 15 divided by 3. So theta is equal to simply the sample mean. So we can say that this expression is minimized at the sample mean. As we have seen over here, sample mean was 5. So we can see that this expression is minimized at this sample value, sample mean value, which is 5. Confidence interval. A point estimator may not be meaningful without knowledge of the probability of how far away it is from the true value. Hence, we would also like to know an interval about the estimator theta and theta hat and the probability that the true value theta lies in that interval. So now here our purpose is that to find the interval in which this true value of theta lies. So such an interval for theta is the random interval such that the probability of that this theta true theta lies between is greater than theta 1 and less than theta 2. These are estimated values of theta, and this is the true value of theta is equal to gamma, where gamma is the confidence coefficient. The realized interval theta 1 and theta 2 is the confidence interval. The coefficient alpha is equal to 1 minus gamma is called the significance level. So we can see that significance level is just the opposite of alpha. 1 minus gamma is equal to alpha. So we just simply subtract gamma, the confidence interval, from 1 and we get the significance level. If n is large enough, we can assume that mu x, which is the mean, is Gaussian distributed with variance sigma square over n. We will find the confidence interval under the assumption that sigma square is known, means the variance is known. The standard normal or Gaussian random variable z is given by z is equal to estimated value of mean minus actual value of mean divided by sigma square divided sigma x divided by under root n. For a confidence coefficient gamma is equal to 1 minus alpha, we can write probability that z is within the interval of z alpha by 2 and z 1 minus alpha by 2 is equal to 1 minus alpha, which is equal to gamma. And if we replace this z with this given z over here, then this equation becomes like this. And we have split the significance level equally on both sides of the density function. As you can see that this is half is plus alpha by 2 and half is 1 minus alpha by 2. For example, the Gaussian table, the z value for 95% confidence R z is 0.025 is equal to 1 minus 19566 and z 0.975 is equal to 1.9556. So you can see over here, if we assume we want to see that what for confidence level 95%, z, the value of z is minus 1.95996 and plus 1.9556. You can see that all these values are positive and negative because we have used this split the significance level equally on both sides of the density function. And the probability that z is less than equal to z, this value is 0.025. Now, as we have said over here, that the confidence interval under assumption that variance is known, sigma square is known. Now we look at the case where this variance is not known, this sigma square is not known. Since the true variance is known in very few cases, we assume we use the estimated variance sigma square. So sigma square hat is the estimated variance. Instead of the actual or true value of variance, we use estimated variance. So in that case, we replace this z with t, and here we use sigma hat. You can see this equation over here. T is equal to mu hat minus mu x divided by sigma x hat divided by under root n is similar to this one. The only difference is that here we are using true value of variance, and here we are using estimated value of variance. And this is called student t distribution with n degrees of freedom. A confidence interval is a way of using a sample to estimate an unknown population value. So what we do is that we use confidence interval to estimate unknown population value from the sample. We use samples values, and we estimate the unknown population value with the help of confidence interval. For estimating the mean, there are two types of confidence intervals that can be used: z intervals and t intervals. And as we have seen that we use z interval when the variance is known, and t intervals when variance is not known. So the z interval estimation is x, this is the mean value, plus minus z critical value, sigma divided by under root n. Z critical value is from the normal distribution and n is the sample size. Common values of ZC from Gaussian table we have seen before is 90% is one critical value is 1.645, 95% 1.96, and 99% is 2.575. You can say 99% is 2.575, and 90% is 1.6, and so on. Example of CI using z-score. How do we use confidence interval? And for that we will see an example. Suppose that in a sample of 50 college students in Illinois, the mean credit card debit was $346. So what we have done is that there are thousands of students in Illinois, maybe university or some institute, and we have just taken a sample of 50 students. Out of those thousands of students, we have taken a sample of 50 students, and the average credit card debt was $346. Maybe, of course, for not it is not the it is not that every student has got $346 debt. It varies. Maybe someone has got $500 debt, somebody has got $400 debt, and something like that. But when we take the average of all these 50 students, it is $346. Suppose that the population standard deviation of credit card debts for this group is $108. Now this sigma is given to us, which is $108. This is standard deviation of the population. Now calculate a 95% confidence interval for the mean credit card debt of all college students in Illinois. So we know the given mean is $346 plus minus 1.96. From where we have got this 1.96, from this 95%. Because if we look at this 95%, ZC is equal to 1.95. 1.95996. So if we round it, then we get 1.96. So plus minus 1.96, 108 is the value of sigma given in this problem, and the size of the population is 50. So the plus minus indicates that we need to perform two different operations, subtraction and addition, Left hand endpoint 346 minus 1.96, 108 divided 50 is equal to 316.1, and right hand gives us 346 plus 1.96, 108 divided 50 is equal to 375.9. So this gives our 95% confidence interval for mu. The population mean is as 316.1 and 375.9. So what is the interpretation? We are 95% confident that the mean amount of the credit card for all college students in Illinois is between $316.1 and $375.9. So what we have calculated over here, that we know that the mean credit card averages from this sample of 50 students is 346. But of course, this 346 is not the actual mean of the population. We do not know the mean of the population, means that of all the students. But we know the standard deviation of the population. So from the standard deviation of the population, we can find the mean interval of mean for the population. We cannot calculate the actual mean value, but we know that what we can calculate is that the range of values in which this actual mean value of the population will lie. So the actual population mean value of the population will lie between $316 to $375. And how much we are confident about that? It will lie between these values. We are 95% confident. So we are 95% confident that the average of the population will be between $316 to $375 for all the students in the Illinois Institute. Example of confidence interval using t-score. So confidence interval is equal to x, the mean value, plus minus t-score into s over n. So it is very much similar to this previous one. The only difference is that there we were using z-score, now here we are using t-score. The value of t-score depends on the sample size through the use of degree of freedom, where df is equal to n minus 1. Now we look at the example of CI using t-score. Suppose that a sample of 38 employees at a large company were surveyed and asked how many hours a week they thought the company wasted on unnecessary meetings. So it's a large company, the number of employees must be large as well. So out of those many employees, we have just asked 38 employees. And what the question was, that how many hours are wasted on unnecessary meetings, in their opinion. So the mean number of hours these employees stated was 12.4. So somebody said maybe 2 hours, somebody said 5 hours, somebody said 20 hours, something like that. But when we calculated the average hours, it was 12.4, and with a standard deviation of 5.1. Calculate 99% confidence interval to estimate. So what we want, that is whatever the range of mean we are going to calculate, the confidence interval should be 99%, very high confidence interval. To estimate the mean amount of time all employees at this company believe is wasted on unnecessary meetings each week. Now, here you can see that this standard deviation given in the example is 5.1, but it is the standard deviation of the sample, not the population. So we cannot use z-score over here, because this standard deviation is the standard deviation of population. When we know the standard deviation of the population, we can use z-score. But when we do not know the standard deviation of the population, but the standard deviation of sample, we have to use t-score. In that case, we have to estimate the standard deviation of the population. So we have a large sample, n is equal to 38, but we only have the sample standard deviation. S is equal to 5.1 is the standard deviation of the sample, not the population. Thus, we will use t interval since this variance, the standard deviation is unknown. To know which row in the t table to look at, we find the degrees of freedom, which is n minus 1 is equal to 38 minus 1 is equal to 37. So to find the degree of freedom is very easy. We simply use, we subtract 1 from the total sample values. So we get the degrees of freedom, which is 37. So if we look at this table over here, in this first column, degrees of freedom is given. So degrees of freedom will be simply whatever the sample size is, subtracted 1. So in this case, it is 37. Next, we have to look at the confidence interval. Here we are looking for 99%. So we will look into the column of 99%, and here it is 2.715. So this t score is 2.715. So we simply use the same method which we have done before. 5.1 divided by under root 38. This gives us the following two endpoints for our interval, left hand endpoint, and we get 10.2 and 14.6. So again, what's the interpretation of these values? We are 99% confident that the mean amount of time that all employees at this company think is wasted on meetings each week is between 10.2 hours and 14.6 hours. The sample was 12.4 hours, but that was the average of the sample, not the population, not of all the employees. Only 38 employees think that way, and that was the average of those 38 employees. Now we cannot calculate the exact average, what is the population, because we haven't asked each and every of them. But what we can say is that it is 99% likely that for all employees, the average will be between 10.2 hours and 14.6 hours. So this is a easy way, because when we do surveys, we have a small sample from the population, and from that sample, we can get the average of the sample. That's easy, but to know the average of the population is difficult. So what we can do is that we can find the a range of values, range of mean values between which we can expect that this average value will lie for the population. Now, hypothesis testing. In point estimation, we have estimated a single value of the unknown parameter, and confidence interval we have determined a range of possible values within an interval. This is what we have done so far. Now we look at a special case. Sometime some information regarding the unknown parameter of the population is available, but we have to test that information with help of a sample. So in this case, what we are saying is that some information regarding the unknown parameter is known. Some information regarding the unknown parameter is known, but we have to test the information with help of sample. So here in hypothesis testing, we are testing the information which is regarding that unknown parameter of the population. So this is the purpose of hypothesis testing, to test the information which is regarding the unknown parameter of the population. In that case, we use hypothesis testing. Furthermore, many probability models require us to make decisions about populations based on limited knowledge. So we have got to make decisions as well sometimes based on those probability models, and the knowledge is very limited. For example, a physician has to make a decision based on knowledge of her patient whether to give a particular drug. Usually this decision is binary in nature, that is to give the drug or not to give the drug. Thus we have a decision problem as opposed to an estimation problem. Here in this case we are making a decision rather than estimating it. Such decision problems come under the category of hypothesis testing. So we use hypothesis testing for two purposes. One is that to test the information regarding the unknown parameter of the population, and second is that to make the decision. In statistics, a hypothesis test calculates some quantity under a given assumption. The result of the test allows us to interpret whether the assumption holds or whether the assumption has been violated. Either the hypothesis is accepted or it is rejected. Level of confidence. Level of confidence tells us that how confident are we in our decision. Suppose we say that the level of confidence is 99% and we decide to reject a hypothesis, then it means we are 99% sure that we have made the right decision. Hence, the level of confidence should be high to make the right decision. So it is something very common sense that whenever we try to make the decision, we want to be sure about it. So the confidence level should be high. When we make a decision, the confidence level should be high, whether we reject the hypothesis, whatever we have assumed before, or we accept it. If we accept our assumption or we reject our assumption, in both the cases we have got to be sure about it. So the confidence level should be high. When we reject or accept hypothesis, then it is possible that we have made wrong decision. In other words, we have wrongly rejected a hypothesis while it was true, or we have wrongly accepted a hypothesis while it was false. So if we reject a null hypothesis that is actually true, then we have made a type 1 error which is called alpha. So alpha is a type of error which is called type 1 error, and this type of error tells you that you have rejected a hypothesis whereas it was actually true. On the other hand, if we accept the null hypothesis, then when it is in fact false, then we have made a type 2 error which is called beta. So basically alpha and beta are the type of errors. Alpha is rejection of hypothesis while it was true, and beta is accepting the hypothesis while it was actually false. The single most important decision principle of the test is to control the probability of type 1 error to keep it below some fixed probability. So when we design a test, what our objective is that to keep the type 1 error in control, means that it should be below some fixed probability. This probability of error, which is denoted alpha, is called the significance level of the test. As we know that significance level is opposite of confidence level. So if confidence level is high, it means significance level is low. Let's say if confidence level is 95%, then significance level is 5%. So level of significance is the complement of the level of confidence. Alpha is equal to 1 minus level of confidence. We have seen this before as well. There are two kinds of hypotheses, simple and composite. A simple hypothesis is one in which the parameters are specified exactly. If they are not, it is called composite hypothesis. A null hypothesis is almost always simple. For example, H naught is equal to theta naught is simple, whereas H naught greater than theta naught is composite. So because H naught is equal to theta naught is exactly specified, we know that this is it is exactly equal to theta naught. But when we say that H naught is greater than theta naught, we do not know the exact value, actual value. Greater than theta naught can be any value. So in that case, we call it composite hypothesis. In testing hypotheses, we usually control the significance level alpha a priori and try to minimize type 2 error beta. We assume a fact based on past information. This fact is called the null hypothesis. So on the whatever information is we already have with us, on that information, based on that information, we make a hypothesis, and that hypothesis is called null hypothesis. If we are interested only in accepting it or rejecting it at a significance level alpha, then it is called significance testing. Here we are accepting it, the hypothesis, or rejecting it based on the significance level only. Then it is called significance testing. On the other hand, we may be interested in postulating an alternate hypothesis H1 and finding methods of accepting H0 or H1. This is called hypothesis testing. So here we have got only one hypothesis, H0, and we accept it or reject it if it's at significance level alpha. On the other hand, there is another type of testing where we have got two hypotheses. One is the first assumed one, that if this is the case, then it's based on the past information, which is called null hypothesis, and there is alternate hypothesis, and finding methods of accepting whether we accept hypothesis A or hypothesis B. We can say that we have got two hypotheses in this case, A and B. So either we have to accept A or we have to accept B. When you have got two hypotheses and we have to make decision between two hypotheses, then it is called hypothesis testing.